Okay, everyone, finishing our last section from Unit 11, which is solving trig equations. Hopefully, we noticed that solving trig equations is just like we were solving an algebraic equation. We follow the same steps. I have those steps over here for you. We want to isolate the trig expression, meaning use inverse operations to get it by itself on one side of the equal sign, and then evaluate. We're solving for theta, and remember theta is an angle measure, so let me put that down here. Solving for an angle measure. And because it's an equation, you can always plug it back in to check when we are done. That's something we'll probably do on a couple of these, okay? Just want you to notice the directions here for numbers 1 through 4 say find all solutions. When we move on to some more complex equations, it's going to be solving the equations for a given domain. And you'll see that domain in these examples when we get there. And I just put a couple different steps there to help you out. Okay, let's start on numbers 1 and 2 though. On number 1, if we're following our steps, we want to isolate the trig expression. And you can treat it just like a variable. So we want to get our tangent trig expression on the same side. So when we subtract from both sides, we have 3 times the tangent of theta minus 1 times the tangent of theta. So we get 2 times the tangent of theta equals 2. Remember, you're just treating this tangent of theta like a variable. Divide by 2. We get tangent of theta equals 1. And now you're just asking yourself the question, what angle measure gets us a tangent trig ratio of 1? Well, that would have to be a 45-degree reference angle in quadrants 1 and quadrant 2, because at 45 degrees our coordinates are root 2 over 2, root 2 over 2. And if you remember, tangent's y over x. So when you put root 2 over 2 over root 2 over 2, we get 1. So 45 degrees is a solution. A 45-degree reference angle here in quadrant 3 would be 225 degrees. But when it wants all the solutions, this is where we need to use n. And hopefully you notice that this just forms a straight line here. So we could just say 45 degrees plus 180 degrees n, where n is any integer. Okay, we don't need to write that every time. Just for the first time is good. So now if you plugged in 1 for n, 45 plus 180 would put you at this angle measure right here. If you add another 180 degrees, you would be back. So you did 180 times 2, you'd be back to this 45-degree reference angle in quadrant 1. And you have all the solutions. There's an infinite number of solutions. Let's plug in the next one to check our solution. We have a little more room on this side. Start by isolating the trig expression. I would start by moving that root 3 to the other side. 2 times the cosine of theta equals negative root 3. Divide by 2. And we're asking ourselves, what angle gets us a cosine ratio of negative root 3 over 2? If we make our unit circle here, negative root 3 over 2, we want our x to be longer than our y. My apologies. So if we want our x to be longer than our y, that's going to be a 30-degree reference angle, and it needs to be in quadrants. It needs to be in quadrants 2 and 3 because that's where x is negative. So unfortunately, this doesn't form a straight line like 45 and 225 degrees. So we just need to say theta equals 150 degrees plus 360 n, and 180 plus 30 is 210 plus 360 n. Okay. And then if you want to plug this back in to check, well, if we plug in, say, 150 degrees for theta, 2 times the cosine of 150 degrees, we know gets us negative root 3 over 2, plus root 3. Hopefully you're going to see we just get negative root 3 plus root 3, which does equal 0, so it checks out. All right, why don't you guys pause the video and try numbers 3 and 4, and I will put the solutions up when you guys are done. For number 3, you should have gotten theta equals 30 degrees plus 360 n, and theta equals 150 degrees plus 360 n. Okay, for number 4, you should have gotten theta equals 60 degrees plus 360 n and 300 degrees plus 360. And for the sake of time, I'm not going to do both. I want to show you one other way you could solve these. You could just replace this cosine of theta with x. 6x minus 1 equals 2. Solve the equation until you have x by itself. 6x equals 3. Divide by 6. X equals 1/2. And then just substitute the cosine of theta back in. Cosine of theta equals 1/2. Well, my x is 1/2 when I'm in quadrant 1 and I have a 60-degree reference angle, and when I'm in quadrant 4 and I have a 60-degree reference angle. Those were our two answers down here. Okay, so if you want to try that trick on some of these, feel free, because we're going to move on to some more complex equations where we have to use some of our trig identities. Okay, so these are really the steps, the same steps as above, except you might need to use some trig identities when you have unlike terms. Okay, and I say factor because hopefully you notice we have a squared in here. So you guys can treat this equation like x squared minus 2x equals 3. We've solved these all year. You're going to have more than one answer. We're going to have to solve by factoring. So let's follow our steps. We want to set the equation equal to 0. So that would mean sine squared theta minus 2 sine theta minus 3 equals 0. And then we're going to solve by factoring. There's no GCFs here, no like terms, or no like factors. So then we're going to factor by grouping, or just making this trinomial two binomials. So sine of theta, just like putting x and x. And then you're looking for factors of -3 that add up to -2, which would be -3 and +1 equals 0. And then you just want to set both equal to 0. So sine of theta minus 3 equals 0. Sine of theta plus 1 equals 0. We get no solution for this binomial, right? Nowhere are we going to get a sine ratio that's greater than 1. This would be no solution. You could check on your calculator. You could punch in inverse sine of 3. You're going to get no solution. But there's definitely a place on our unit circle where we have a sine ratio of -1, right? That would be over here at 0, -1. That would be over here at positive 270 degrees. It wants your answers, however, in terms of pi, so that is in terms of radians, so that's 3 pi over 2 for theta. One solution here. Sorry, I didn't mean to steer you the wrong way in saying there's always going to be multiple solutions. In this case, there's just one. In some cases, you'll have more than one. Okay, let's try another. This is a perfect example of step 2 when you have unlike terms. Because if you're looking at this equation, we have cosine and sine. And we're not going to be able to solve an equation when we have unlike terms. That's like having x and having y. So what we want to do is we want to get this cosine squared theta in terms of sine. So let's follow our steps, get everything on the same side, set it equal to 0. Okay. And now if you look at these identities that we wrote down from 11.3, hopefully you can see this first Pythagorean identity, having cosine squared plus sine squared equaling 1. That's a way to get cosine or sine in terms of the other ratio. So we can just say that cosine squared theta equals 1 minus sine squared theta by just moving that to the other side. And now we can replace this cosine squared theta with 1 minus sine squared theta. And now we are in terms of sine. We have like terms. We're ready to solve. Let's distribute 2 minus 2 sine squared theta minus sine theta minus 1. We want to combine our like terms. 2 minus 1 leaves us with 1. And then what I like to do whenever that leading coefficient's negative, I like to factor out the negative. So take out the negative, and now we have 2 sine squared theta plus sine theta minus 1. And this should be a little bit easier for us to factor. 2 sine theta needs to be with one of our first binomials, sine theta with the other. And then this last term's negative, so you need a negative 1 and a positive 1, and then just use guess and check to see if this works. By foiling, we get 2 sine squared theta plus 2 sine theta minus sine theta, which is going to give us positive sine theta, and then that minus 1 at the end. So it does check out. We're good. Now our last step is to set them both equal to 0. These are both going to get us, so sine of theta equals 1/2 and sine of theta equals negative 1. These are both going to get us solutions. Sine of theta equaling 1/2 is a solution if our domain is restricted to the whole circle. That would be a solution in two places where the y is positive 1/2. Right here at a 30-degree reference angle, and over here in quadrant 2 at a 30-degree reference angle, and then the negative 1 we did on the previous problem. That was 270 degrees, or 3 pi over 2. And then for our 1/2 was at 30 degrees. Sorry, let's put this in radians. So that would be pi over 6 and 5 pi over 6. We got some room on here, so let's test one of these solutions. Let's plug in pi over 6. So that would look like this. 2 times the cosine of pi over 6 squared equals sine times the pi over 6, sine of pi over 6 plus 1. Okay. The cosine of pi over 6, if the sine of 1/2, or if the sine of pi over 6 is 30, we know that, we just solved that. Sorry, if the sine of pi over 6 is 1/2, then for pi over 6, that would be our root 3 over 2. But keep in mind, it's root 3 over 2 squared. So that gives us a positive 3 over 4 times 2. And 1/2 plus 1. This is going to check out because 2 goes into 4 twice. So we get 3 over 2 equals 3 over 2, and that checks out. Okay. Don't worry about checking every single one of these. I just wanted to show you a couple times on this lesson so you are reminded that we're just solving equations here. You can plug these solutions back in to check and evaluate and make sure the equation is true. All right, why don't you guys try the next two? Try 3 and 4. Actually, try the next 3. Try 3, 4, and 5. I'm going to put the solutions up. I'm not going to work through all of them with you for the sake of time. If you want to go over these 3 practice problems, we can during the Google Meet. And then we're going to finish doing 2 more together, 6 and 7. So pause the video, try 3, 4, and 5. I'll put a little hint on here on 4 and 5. You need to, you have unlike terms, so use trig identities to get like terms. Okay, that's the same for both of these. Use your trig identities to get like terms, and then look at your domain restriction if you want your answer in terms of degrees or radians. All right, pause the video, work these out, and I'll put the solutions up when you're done. Number 3, theta should have equaled 2 pi over 3, and 0 is included, so 0 pi radians as well for your 2 solutions. For number 4, I'll just kind of show you this first step. You wanted to rewrite sine squared theta as 1 minus cosine squared theta plus 4 cosine theta minus 5. equals 0. I'll kind of jump down and show you what this should have looked like when you factored. You should have had 2 cosine theta minus 1 and 2 cosine theta minus 1, because you could have taken out a GCF here. When you FOIL this, or sorry, you weren't going to be able to take a GCF out here. It was going to look like a perfect square trinomial, which is why you have these 2 binomials here. So you just have one of these equations equal to 0 because it's the same thing. So you would have gotten theta equals 60 degrees or 300 degrees. Remember, degrees because your domain is restricted in degrees. And then I'll show you the same for 5. You wanted to rewrite secant as tangent, and you could have done that using this trig identity right here. Secant squared theta equals 1 plus tangent squared theta. So we could have rewritten this as tangent squared theta plus 1 plus tangent squared theta. Yeah, perfect. 1 plus tangent squared theta equals 3. Okay, this was going to be our problem where you could take out a GCF, because after combining like terms and moving the 3 to the other side, minus 3 equals 0, you were left with 2 tangent squared theta minus 2 equals 0. GCF, both of these terms have a 2. So you could have taken out the 2, you're left with tangent squared theta minus 1. This is a difference of 2 squares, so tangent of theta minus 1 times tangent of theta plus 1. And you are going to get a couple answers here. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Answers are in radians because our domain is restricted in radians. These were all pi over 4 because when you set them equal to 0, you're going to get tangent of theta equals plus or minus 1. And we had a problem like that early in our notes when we know that needs to be a 45-degree reference angle, or pi over 4 reference angle. All right, let's do the last 2 together. I don't think there's any like these last 2 on the homework. These are pretty difficult, but one of these is a no solution, and one you cannot. Both of these you can't factor, which is why I wanted to finish with these 2. Okay, if we're following our steps, we get cosine squared theta plus 2 times cosine of theta minus 1 equals 0. Because you can't factor, you're going to need a calculator, so I'm going to pull that up if I can. Okay. Oh, come on. There we go. So right away we notice we can't factor. There's no factors of -1 that add to +2. So hopefully we remember this, and I don't plan on putting any of these on the quiz for you. Maybe I'll add one as an extra credit problem. But A is 1, B is 2, C is -1. You need to use your quadratic. Negative B plus or minus the square root of B squared minus 4AC all over 2A. Hopefully it's all coming full circle for us. All right, our B is 2. So -2 plus or minus the square root of 4 minus 4 times 1 times -1 all over 2 times 1, so 2. So we get -2 plus or minus the square root of 8, which simplifies to 2 root 2. Don't forget, for 8, you need to factor down and pull out your pair of 2's when you simplify radicals. Now when we break this up, we get -1 plus or minus the square root of root 2. Okay, the way we evaluate using our calculator is this would mean that the cosine of theta equals -1 plus root 2, and the cosine of theta equals -1 minus root 2. Well, there's a problem with this second ratio. because negative 1 minus root 2 is a integer greater than 1. And anytime that's the case for sine and cosine, there's no solution. You can check by doing second cosine, negative 1 minus root 2, and you're going to see problem. That's undefined. So no solution there. But let's try the plus 2. We do have a solution. We have a solution of 65.5 degrees. Okay, but let's also be careful because we can also have this is a positive ratio because negative 1 plus root 2, that gives you a positive number. You can also have a 65-degree reference angle in quadrant 4 here and getting the same thing, 65-degree reference angle here. So 65.5 degrees, and if you do 360 minus 65.5, we get 294.5 degrees. Two answers here. No solution for this equation because cosine is undefined when our ratio is greater than 1. Okay, probably an extra credit problem on the quiz. Let's do one last one. Our domain is restricted in radians. Get everything on the same side. Cosine squared theta plus 1/2 cosine theta minus 5. We don't have any unlike terms. We didn't on the previous problem. This can't factor, so you need to use your quadratic. We get negative 1/2 plus or minus the square root of b squared, so 1/4, minus 4ac all over 2 times 1. So negative 1/2 plus or minus the square root of 20 plus 1/4. So that's 20 1/4. I'm just going to rewrite that as 81 over 4. 20 1/4 is 81 over 4. I'm going to keep it as an improper fraction over 2. Okay, let's rewrite this now as negative 1/2 over 2 plus or minus the square root of 81 over 4 over 2. Negative 1/2 of 1/2 is 1/4, so negative 1/4 plus or minus, these are both perfect squares, so we get we get 9 over 2 over 2, which is 9 over 4. That's the same as multiplying by 1/2. So we have two answers here. Cosine of theta equals negative 1/4 plus 9 over 4, and cosine of theta equals negative 1/4 minus 9 over 4. Simplify these down. We're looking for a cosine ratio that gets us 9 minus 1 would be our 8 over 4, which is 2. Oh, shoot. Problem, we just talked about cosine ratios never being greater than 1, so this would be no solution or undefined. And then down here, also a problem because we get negative 10 over 4, which is an integer greater than 1, so also no solution. So I just wanted to show you one example where you can have no solution for the entire equation, and that's okay. All right, but for the most part, your homework will consist of problems that are going to have solutions. I don't think there's any where you need to use the quadratic. There might be one that's no solution. If you find that problem and you're stuck on it, we can go over it together on one of the Google Meets. But most of the stuff will be like these 1 through 5. Okay. Don't forget to use these trig identities when you need to get like terms. Don't forget your reference angles, and we can go over any questions you guys have during the Google Meet. Good luck.